Somewhere in the constellation Cygnus, a star 10 times the mass of our Sun collapsed into a point smaller than a city, and the universe folded around it like water swirling toward a drain. This is what we've come to rest beside, not with urgency, not with the need to understand everything at once, but simply to let the strangeness of it wash over us. Slow and distant, the way light itself slows when it wanders too close to such places. There is time here, all the time one could need, to breathe and to drift and to let the mind grow quiet. If these words help carry you towards sleep, perhaps leave a gentle subscribe so that more nights like this one might find you. And now, with nothing asked of you but stillness, let us begin here. On any clear night, far from the glow of city lights, you might step outside and look upward into that vast and ancient darkness, and there you would find the stars, scattered like fine grains of salt across black velvet, each one a distant sun burning steadily in the emptiness of space. They appear fixed and eternal, those points of light, as though they have always been there and always will be, unchanged since the first humans tilted their heads back to wonder at them. The same stars that guided sailors across the Mediterranean, the same constellations that shepherds named while tending their flocks on hillsides in Mesopotamia, the same patterns of light that children trace with their fingers pressed against cold window glass on winter evenings. It is a comforting thought, really, this apparent permanence of the night sky, this sense that some things in the universe remain constant and reliable while everything else shifts and changes around us. And yet, like so many comforting thoughts, this one is only partly true, a gentle simplification that serves us well enough in our daily lives, but does not quite capture the whole of things. The stars, you see, are not eternal at all. They are born. They live out their long and luminous lives, and eventually, in their own quiet way, they come to an end. The timescales involved are simply so vast, so incomprehensibly long compared to a human lifetime or even the entire span of human civilization, that we cannot perceive their changes directly. A star might burn for 10 billion years, which is a number so large that it becomes almost meaningless when spoken aloud. And during the few thousand years that humans have been recording their observations of the sky, that star would appear utterly unchanged, a fixed point of light showing no sign of the slow processes unfolding within its core. But occasionally, very occasionally, the heavens do reveal their impermanence in ways that even ancient observers could not miss. On the 4th day of the 7th lunar month in the year 1054 of the Common Era, astronomers serving the Song dynasty of China recorded the sudden appearance of what they called a guest star, a new point of light that had not been there before. Blazing so brightly in the constellation we now call Taurus that it could be seen even during the day, visible against the bright blue sky for 23 days before finally fading enough that only the darkness of night could reveal it. For nearly 2 years, this guest star remained visible to the naked eye, a temporary visitor in a sky that everyone had assumed was unchanging, before it finally dimmed beyond the threshold of human perception and was recorded only in the careful brushstrokes of court astronomers on silk and paper. Those Chinese astronomers could not have known what they were witnessing, could not have understood that they were watching the death throes of a massive star located some 6,500 light-years from Earth. Its final explosive collapse, sending light racing across the cosmos that would not reach our small planet until those court officials happened to glance upward on that summer night. Today, when we turn our telescopes toward the same patch of sky, we find the Crab Nebula, a beautiful and expanding cloud of gas and dust. The remnants of that stellar death still spreading outward into space after nearly 1,000 years, glowing faintly with the energy of its own dispersal. The star that once burned there is gone now, but its remains drift on, slowly mixing with the thin gas between the stars, carrying with it the heavy elements that were forged in the star's core during its long lifetime and scattered into space during its final moments. This, then, is what we mean when we speak of stellar life cycles, the gentle and inevitable progression from birth to death that governs every star in every galaxy throughout the observable universe. Like living things, though on timescales that dwarf anything biological, stars are born from clouds of gas. They burn through their fuel in the process of living, and eventually they exhaust that fuel and must face whatever end their particular circumstances dictate. It is not a dramatic or frightening process. Really, not when you step back and view it from a sufficient distance, but simply the universe going about its business in the way that it always has, recycling matter and energy from one form to another, building new structures from the remnants of old ones, continuing the endless and patient work of cosmic change. The fuel that stars burn is hydrogen, the simplest and most abundant element in the universe. And they burn it not through any chemical process like the combustion of wood or coal, but through nuclear fusion, the pressing together of atomic nuclei under such tremendous heat and pressure that they overcome their natural repulsion and merge into heavier elements. This understanding came to us relatively recently in the long history of human curiosity about the stars, not arriving in any complete form until the 1920s, when the English astrophysicist Arthur Stanley Eddington began to piece together the puzzle of what powered the Sun and its countless stellar cousins scattered across the night sky. Eddington was a Quaker and a pacifist, a gentleman who spent part of the First World War performing agricultural work as a conscientious objector, and who approached the mysteries of the universe with a quiet determination that suited his temperament. He understood, through careful calculation and observation, that the temperatures and pressures at the cores of stars were sufficient to drive nuclear reactions, and that these reactions could account for the tremendous energy output that stars maintain over billions of years. Before Eddington's work, scientists had struggled to explain how the Sun could have been burning for the billions of years that geological evidence suggested, since no chemical fuel could possibly last so long. But nuclear fusion provided an answer. A vast reservoir of energy locked within the very structure of matter itself, released gradually as hydrogen atoms were pressed together to form helium. And so we can picture a star, any star, as a great and patient furnace, balanced in a delicate equilibrium between two opposing forces. Gravity pulls inward, trying always to collapse the star down into a single dense point, while the pressure of the nuclear reactions in the core pushes outward, resisting that collapse, holding the star up against its own weight. For as long as the fuel lasts, this balance is maintained, and the star burns steadily, pouring light and heat out into the darkness that surrounds it. The length of a star's life depends primarily on its mass, which might seem counterintuitive at first, since one might assume that a larger star, having more fuel to burn, would naturally live longer than a smaller one. But the opposite is true, and the reason lies in the fierce conditions at the cores of massive stars. A star with 10 times the mass of our Sun does not burn its fuel at 10 times the rate, but rather at something like 1,000 times the rate, because the greater gravitational pressure at its core drives nuclear reactions at a correspondingly faster pace. Such a star blazes with extraordinary brilliance, pouring out light and energy at a rate that would exhaust our own modest Sun in a tiny fraction of its natural lifetime. And as a result, these giant stars live fast and die comparatively young, burning through their reserves in mere millions of years rather than the billions that smaller stars enjoy. Our own Sun is a yellow dwarf, a thoroughly ordinary and medium-sized star that has been burning steadily for about 4.5 billion years and has roughly that much time remaining before its fuel begins to run low. When that day finally comes, incomprehensibly far in the future, the Sun will swell into a red giant, engulfing the inner planets and scorching whatever remains of Earth, before eventually shedding its outer layers and collapsing into a white dwarf, a dense remnant about the size of our planet but with the mass of a star, slowly cooling over trillions of years as it radiates away the last of its heat into the darkness. It is a peaceful end. Really, a gentle fading into the long night of cosmic time. And white dwarfs are among the most common objects in the galaxy, the quiet graves of ordinary stars that lived ordinary stellar lives. But for stars significantly more massive than our Sun, those with 8 or more times its mass, a different fate awaits, and the story of their ending is somewhat more complex, though no less natural and no less a part of the universe's ordinary functioning. These massive stars burn through their hydrogen quickly, as we have discussed, converting it into helium through the same fusion process that powers our own Sun. But when the hydrogen in the core is exhausted, the core contracts under gravity's unrelenting pull, heating up as it does so until it becomes hot enough to begin fusing the helium itself into heavier elements still, primarily carbon and oxygen. This pattern repeats itself over and over as the star ages and its core grows ever denser and hotter. The helium is exhausted and the core contracts further, heating up until carbon fusion begins, producing neon and magnesium and sodium. Then the carbon is depleted, and the process continues, with oxygen fusing to produce silicon, and silicon fusing to produce iron. Each stage of fusion occurs in a shell around the core, so that near the end of its life, the star has an onion-like structure, with layers of different elements nested one inside another, the heaviest at the center and the lightest at the outer edges. A testament to the long and patient work of nuclear synthesis that has been going on for millions of years. This process of building heavier elements from lighter ones is called nuclear synthesis, and it is among the most profound discoveries of 20th century physics, for it means that the atoms in our own bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, were forged in the cores of stars that lived and died long before our solar system was born. We are, quite literally, made of star stuff, our very existence dependent on the deaths of ancient suns that scattered their enriched material into the cosmos. But here is a curious fact about iron, the element that sits at the end of this long chain of stellar fusion. Iron is the most stable of all atomic nuclei, the point at which the balance between nuclear forces reaches its minimum energy state. And this stability has consequences that are both elegant and profound. When a star fuses lighter elements into heavier ones, from hydrogen up through the sequence to iron, each reaction releases energy, adding to the outward pressure that supports the star against gravitational collapse. But iron is different. Fusing iron into heavier elements does not release energy at all, but rather absorbs it, sucking heat from the star's core rather than generating it. And so, when a massive star has converted enough of its core material into iron, it finds itself in a predicament that admits no easy solution. The fusion reactions that have sustained it for millions of years can no longer continue in the same way, for there is no more energy to be extracted from building heavier nuclei. The star has climbed the staircase of elements as far as it can go, and at the top of those stairs, it finds an iron core, inert and unable to provide the pressure needed to hold up the tremendous weight of the star's outer layers. What happens next unfolds with a swiftness that would seem almost startling after the slow processes that preceded it, though even this final act takes place over timescales that are quick only by stellar standards. The core, no longer supported by the outward pressure of fusion, begins to collapse under its own gravity, and this collapse happens fast, the iron core falling inward at a significant fraction of the speed of light, compressing and heating as it goes. The electrons in the iron atoms are squeezed into the protons, forming neutrons and releasing a flood of nearly massless particles called neutrinos that stream outward through the collapsing star. The outer layers of the star, suddenly deprived of the support that the core once provided, come crashing down as well, falling inward toward the center, accelerating under gravity's pull, until they meet the resistance of the now incredibly dense core and bounce outward again in a tremendous shockwave that tears the star apart. This is a supernova, the explosive death of a massive star, an event so energetic that for a brief time it can outshine an entire galaxy, releasing more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. It was such an event that those Chinese astronomers witnessed in 1054, the sudden brightening of a star too far away to be seen under normal circumstances, made temporarily visible by the violence of its own destruction. And it is such events, repeated countless times over the history of the universe, that have enriched the cosmos with heavy elements, scattering the products of stellar nuclear synthesis into the vast spaces between the stars, seeding the clouds of gas from which future generations of stars and planets will form. This is the universe's natural recycling, really, the quiet and ongoing process by which matter is transformed and redistributed, broken down and built back up, cycled through stars and space and back again over timescales that make human concerns seem wonderfully small and brief. A massive star burns bright, fuses its fuel into heavier elements, and then, when it can no longer sustain itself, it returns those elements to the cosmos, giving back what it once gathered from the primordial gas, enriched now with the products of its own nuclear fires. And for some stars, the most massive of all, even this is not the end of the story. When the core that remains after the supernova is massive enough, when too much material is left behind for even the pressure of neutrons packed tight against one another to resist gravity's final victory, then something else happens, something quieter and stranger still, a final collapse from which nothing, not even light itself, can escape. But that is a subject for another moment, another gentle exploration of the universe's darker corners. For now, it is enough to rest with the knowledge that stars are born and stars die, that this has always been so and will continue to be so for as long as there is matter in the universe to be gathered and burned, and that in this great cosmic cycle of creation and destruction, there is nothing to fear, only the patient and beautiful unfolding of natural law across the endless reaches of space and time. When you were young, perhaps you threw a ball into the air and watched it rise. Slow. Pause for a moment at the peak of its journey, and then return softly to your waiting hands. There was nothing remarkable about this, nothing that seemed to contain within it the seeds of cosmic mystery. And yet, that simple arc, that gentle curve of a ball rising and falling, holds within it one of the most profound questions we can ask about the universe. The ball rises because you gave it energy, because your arm transferred motion into that small sphere, and it falls because the Earth, patient and immense beneath your feet, was pulling it back all along. The Earth never stopped pulling, not for a single moment, and so the ball, having spent all the energy you gave it, had no choice but to return. This is the way of things on our world, this constant conversation between motion and gravity, between the desire to rise and the gentle insistence to fall. If you were to throw that ball a little harder, it would rise a little higher before returning, harder still, and it would climb further into the sky, perhaps disappearing briefly from sight before arcing back down to the ground somewhere in the distance. You might begin to wonder, lying there in the quiet of the evening, whether there is some speed, some particular swiftness of throw, that would allow the ball to rise and never return at all. And the answer, which scientists worked out long ago through careful thought and patient mathematics, is yes. There is such a speed, and we call it the escape velocity. It is not a complicated idea at its heart, merely the speed at which an object must travel to break free from the gravitational embrace of whatever body it is leaving, to rise and keep rising, never to fall back, sailing outward into the darkness between worlds. For our Earth, this speed is approximately 11.2 kilometers per second, which is to say roughly 40,000 kilometers per hour, a velocity so great that no human arm could ever achieve it. No ball thrown by hand could ever reach it. And yet rockets do reach it, climbing on pillars of fire and noise until they have given their payloads enough speed to slip free of our planet's hold. When a spacecraft leaves Earth to visit the Moon, or Mars, or the distant outer planets, it must first achieve this escape velocity, must first win the quiet argument with Earth's gravity, and only then can it coast outward into the void. The heavier the world, and the smaller its radius, the faster you must travel to escape it. And this relationship between mass and size and the speed of leaving is something that occupied the minds of natural philosophers long before rockets existed, long before we had any means of leaving our world at all. In the year 1783, in the county of Yorkshire in the north of England, there lived a rector named John Michell, a man of the church who was also a man of science, which was not unusual in those days when the boundaries between disciplines were softer and more permeable than they are now. Michell was a Fellow of the Royal Society, a geologist who had written about earthquakes, a maker of scientific instruments, and a thinker who spent his quiet hours contemplating the nature of light and gravity. He was not famous in his own time, not in the way that Newton had been famous, or that his contemporaries in the great cities were famous, and he lived out his days in relative obscurity, tending to his parish and his thoughts in equal measure. And yet, this country rector, this unlikely cosmic pioneer, wrote a letter in 1783 to his friend Henry Cavendish. And in that letter, he proposed an idea so strange and so far ahead of its time that it would take more than a century for the world to truly understand what he had imagined. Michell understood Newton's theory of gravity, as any educated man of science would have in those days. He understood that every object with mass pulls on every other object with mass, that this pull grows stronger as objects grow more massive, and that it grows weaker as they move further apart. Newton had described this relationship with elegant mathematics, showing that the gravitational force between two bodies depends on the product of their masses divided by the square of the distance between them, all multiplied by a constant that describes the fundamental strength of gravity itself. This inverse square law, as it came to be known, explained the motions of planets around the sun, the fall of apples from trees, the tides of the ocean, and 1,000 other phenomena that had puzzled humanity since the beginning of recorded thought. Gravity, Newton showed, was universal, acting the same way on Earth as it did in the heavens, binding the cosmos together with invisible threads of attraction. Michell took this understanding and combined it with the knowledge, already established by that time, that light travels at a finite speed. Light was fast, extraordinarily fast, faster than anything else anyone had ever measured, but it was not infinitely fast. And this meant that light, whatever it truly was, must have some relationship with the physical world, must obey some of the same rules that governed other moving things. And here Michell made his great leap of imagination. If light had a speed, and if gravity could slow things down, pulling them back toward massive bodies, then could there exist a body so massive, so dense, so overwhelming in its gravitational pull that even light itself could not escape from it? Could there be stars that were dark, not because they did not shine, but because their light could never leave them, forever trapped in the grip of gravity, forever falling back even as it tried to fly away? Michell calculated what such a body would have to be. Using the mathematics of his day, assuming that light behaved like a small particle subject to gravitational attraction, he worked out that a star with the same density as our Sun, but with a diameter 500 times greater, would have an escape velocity equal to the speed of light. From such a star, Light could rise and rise, but never quite escape, asymptotically approaching freedom, but never achieving it, forever bound to that immense dark sphere. We would not see such stars, Michel reasoned, because no light from them would ever reach our eyes. And yet, they might still exist, revealed only by their gravitational effects on nearby visible stars, pulling on their luminous neighbors while remaining themselves forever hidden in darkness. This was a remarkable idea, proposed by a rector in Yorkshire, written in a letter to a friend, and then largely forgotten for many years. Michel died in 1793, 10 years after writing that letter, and the world moved on without much notice of his dark stars. But ideas have a way of resurfacing, of being independently discovered by other minds working on similar problems. And so it was that in 1796, the French mathematician Pierre-Simon Laplace, working in Paris, reached conclusions remarkably similar to those Michel had reached in Yorkshire. Laplace was one of the greatest mathematicians of his age, a man who would come to be called the Newton of France. And in his monumental work on celestial mechanics, he briefly discussed the possibility of corps obscurs, or dark bodies, objects so massive that light could not escape them. Like Michel, Laplace imagined these bodies as extreme cases of ordinary gravitational physics, stars that had crossed some threshold of density beyond which visibility became impossible. Neither Michel nor Laplace had the complete picture, of course. They were working with Newton's theory of gravity, which we now know to be an approximation, accurate for everyday situations, but incomplete in the presence of extreme masses and velocities. They treated light as if it were a stream of tiny particles subject to gravitational attraction in the same way that planets and moons are, which is not quite correct either. And yet, their fundamental insight, that there could exist objects so compact that even light cannot leave them, was sound, and it anticipated by more than a century the rigorous predictions of general relativity. In their quiet studies, by candlelight and firelight, these men glimpsed something that would not be fully understood until Einstein reformulated our understanding of space, time, and gravity itself. And so we arrive at the question that might drift through your mind as you settle deeper into your pillow. The question that Michel and Laplace asked in their own ways more than 200 years ago. Could there truly be objects in the universe so dense, so concentrated in their mass, that even light, traveling at 299,792 kilometers every second, cannot break free from them? Light, which crosses the room in a time too short to measure, which travels from the sun to the earth in just over 8 minutes, which can circumnavigate our entire planet more than 7 times in a single second. Could something hold even this, the fastest thing there is, the ultimate speed limit of the universe, prisoner forever? The answer, as we now know from both theory and observation, is yes. Such objects do exist. They are real features of our universe, scattered throughout the cosmos, lurking at the centers of galaxies, drifting through the spaces between stars, the collapsed remnants of the most massive suns. But that is a story for later, a path we will walk down in the sections to come, and for now, it is enough to let this impossibility settle gently into your thoughts. There are places in the universe from which nothing returns. Not matter, not radiation, not light itself. And the first glimmers of this understanding came from a country rector in Yorkshire and a mathematician in Paris, working by the feeble glow of early modern science, reaching across the centuries to touch the edges of something vast and strange. The speed of leaving, then, is not just about rockets and balls thrown into the air. It is about the fundamental relationship between motion and gravity, between the desire to go and the insistence to stay. And when that relationship reaches its extreme limit, when gravity becomes so powerful that no speed is fast enough, something new and strange emerges, something that Michel called a dark star and that we now call by a different name. A name you almost certainly know, a name that captures both the darkness and the mystery of these impossible objects. But for now, let the idea simply rest. Let it settle into the quiet spaces of your mind as you drift toward sleep, knowing that the universe contains wonders beyond easy comprehension, and that even the simple act of throwing a ball into the air connects you, however faintly, to the most extreme and hidden places in all of existence. In the year 1915, while the fields of Europe lay torn and scarred by the most devastating conflict humanity had yet known, a quiet revolution was unfolding in the realm of physics, one that would eventually lead us to understand these peculiar objects we have been gently exploring together. Albert Einstein, working in Berlin, published his general theory of relativity in November of that year, presenting to the world a vision of gravity so fundamentally different from anything that had come before that it would take decades for its full implications to be appreciated. The trenches of the Western Front stretched from the English Channel to the Swiss border, and millions of young men faced each other across landscapes of mud and barbed wire. Yet, in the midst of this unimaginable destruction, the human mind continued its patient work of understanding the cosmos. Einstein had been laboring on this theory for nearly a decade, refining his ideas, correcting his mathematical errors, and gradually building a framework that would replace the gravitational theory Newton had constructed more than 2 centuries earlier. Where Newton had described gravity as a force acting instantly across the void of space, an invisible pull between masses, Einstein proposed something far more elegant and, in its own way, far more strange. In his conception, gravity was not a force at all, but rather a consequence of the geometry of the universe itself. Space and time, which had long been considered separate and unchanging stages upon which the events of the cosmos played out, were revealed to be woven together into a single fabric, a 4-dimensional continuum that Einstein called spacetime. And this fabric could bend and stretch and curve in response to the presence of mass and energy. To help us understand this idea, which can seem rather abstract when described in purely mathematical terms, physicists often invite us to imagine a simple demonstration, one that you can picture quite easily as you rest there now. Imagine a large sheet of rubber, perhaps the sort used for a trampoline, stretched taut and held level at its edges. If you were to place a heavy bowling ball in the center of this sheet, the rubber would sag downward, creating a curved depression around the ball. Now imagine rolling a marble across the surface of this sheet. If the marble passes close to the bowling ball, it will not travel in a straight line, as it would on a perfectly flat surface, but will instead curve toward the bowling ball, following the contour of the depression in the rubber. The marble appears to be attracted to the bowling ball, drawn toward it by some invisible force, but in reality, it is simply following the curved geometry of the surface, taking the most natural path through a landscape that has been warped by the presence of mass. This analogy, while imperfect in several respects, captures something essential about Einstein's vision of gravity. The Sun, sitting at the center of our solar system, curves the spacetime around it, and the planets, including our own gentle Earth, follow paths through this curved spacetime, orbiting not because they are being pulled by a force reaching across empty space, but because they are traveling along the most natural routes through a universe whose very geometry has been shaped by the Sun's mass. The mathematics that Einstein developed to describe these curves and paths is called the Einstein field equations, a set of interlocking relationships that connect the distribution of mass and energy in any region of space to the curvature of space-time in that region. These equations are notoriously difficult to solve, requiring considerable mathematical sophistication, and Einstein himself initially believed that exact solutions might be impossible to find. Yet, within weeks of Einstein publishing his theory, while the guns still thundered along the fronts of Europe, a solution emerged from an unexpected quarter. Karl Schwarzschild was a German astronomer and physicist of considerable brilliance, a man who had made important contributions to the study of stellar atmospheres and the optics of astronomical instruments. In December of 1915, Schwarzschild was serving as an artillery officer in the German army on the Russian front, calculating trajectories of shells and enduring the hardships of that brutal campaign. And yet, he found time, in whatever quiet moments were available to him, to work through the mathematics of Einstein's newly published equations. Within those cold weeks near the end of the year, working by lamplight in conditions we can scarcely imagine, Schwarzschild found an exact solution to the field equations, describing the curvature of space-time around a perfectly spherical, non-rotating mass. This solution, which would come to bear his name, was elegant and precise, and it revealed something rather peculiar in its mathematical structure. Schwarzschild discovered that for any given mass, there existed a critical radius at which the equations behaved in a very strange manner, a boundary that would later come to be known as the Schwarzschild radius. To understand what this boundary represents, we must return for a moment to the concept of escape velocity that we touched upon earlier in our narration. As you may recall, every massive body has an escape velocity, the speed at which an object must travel to break free from that body's gravitational influence. For the Earth, this speed is approximately 11 kilometers per second, and for the Sun, it is considerably higher, around 617 kilometers per second from its visible surface. What Schwarzschild's mathematics revealed was that if you were to compress any mass into a sufficiently small volume, there would come a point at which the escape velocity at its surface would equal the speed of light itself. The speed of light, as Einstein had established in his earlier work on special relativity, represents an absolute cosmic limit, a velocity that nothing bearing mass or information can exceed. If the escape velocity at some surface equals the speed of light, then nothing, not matter, not light, not any form of energy or signal whatsoever, could escape from within that boundary. Schwarzschild had found, hidden within the elegant curves of Einstein's equations, a mathematical description of the very phenomenon that John Michel and Pierre-Simon Laplace had imagined more than a century before, a region of space from which nothing could return. For the Sun, the Schwarzschild radius works out to be approximately 3 kilometers. This means that if you were somehow to compress the entire mass of the Sun into a sphere just 3 kilometers across, its surface gravity would be so intense that light itself could not escape. For the Earth, the corresponding radius is roughly 9 millimeters, smaller than a marble. These numbers seemed, to the physicists of the time, to be nothing more than mathematical curiosities, interesting features of the equations that surely had no bearing on physical reality. No one could imagine a mechanism by which matter might be compressed to such extraordinary densities, and the idea that such objects might actually exist in the universe seemed quite fantastical. Schwarzschild sent his solution to Einstein in January of 1916, and Einstein presented it to the Prussian Academy of Sciences shortly thereafter, expressing his admiration for the elegance of the work. Tragically, Schwarzschild would not live to see the implications of his discovery unfold. While serving on the Russian front, he had developed pemphigus, a rare and painful autoimmune condition in which the body's immune system attacks the skin, causing blistering and lesions that do not heal. He was invalided home from the front, but the disease progressed relentlessly, and in May of 1916, just 5 months after solving Einstein's equations, Karl Schwarzschild died at the age of 42. His solution remained a gift to physics from a man who had found time for pure mathematics amid the chaos of war, and it would prove to be one of the most important results in the history of gravitational theory. Einstein himself was deeply skeptical that the strange features of Schwarzschild's solution could have any physical meaning. Throughout his life, Einstein returned again and again to the question of whether objects corresponding to the extreme predictions of his equations could actually exist, and he consistently concluded that they could not. In a paper published in 1939, Einstein argued that the angular momentum of matter, its tendency to spin and rotate, would prevent any realistic collapse from reaching the Schwarzschild radius. He believed that some physical process, some pressure or force that we had not yet fully understood, would always intervene to halt the collapse before the point of no return was reached. This view was widely shared among physicists of the era, and for many decades, the Schwarzschild solution remained a theoretical curiosity, studied for its mathematical interest, but not taken seriously as a description of anything that might actually exist in the night sky. Yet, even as doubt surrounded the extreme implications of general relativity, the more modest predictions of the theory were being tested and confirmed. In 1919, a British expedition set out to observe a total solar eclipse, with the goal of measuring whether light from distant stars was bent as it passed close to the Sun, as Einstein's theory predicted. The expedition was led by Arthur Eddington, a Quaker and pacifist who had been a conscientious objector during the war and who had championed Einstein's work in Britain even while the two nations were enemies. Eddington travelled to the island of Principe, a small volcanic island off the western coast of Africa, while a second team journeyed to Sobral in Brazil. And on the 29th of May, 1919, both teams photographed the eclipse, capturing images of stars that appeared near the obscured disk of the Sun. The analysis of these photographs took several months, as the positions of the stars had to be compared carefully with their normal positions when the Sun was elsewhere in the sky. But by November of that year, Eddington announced the results. The starlight had indeed been deflected, bent by the curvature of space-time around the Sun, and the amount of deflection matched Einstein's predictions rather than the smaller value that Newtonian gravity would suggest. The announcement made headlines around the world, and Einstein, who had been known only to specialists before, became an international celebrity almost overnight. The confirmation of light bending was a triumph for general relativity, demonstrating that space-time curvature was not merely a mathematical abstraction, but a real feature of the physical universe. In the decades that followed, physicists continued to explore the mathematics of Schwarzschild's solution, mapping out the strange properties of the region surrounding that critical radius. They found that an object falling toward this boundary would, from the perspective of a distant observer, appear to slow down as it approached, its light becoming ever more redshifted, stretched to longer and longer wavelengths by the intense gravitational field. The object would seem to freeze at the boundary, never quite crossing it, fading from view as its light stretched into invisibility. Yet, from the perspective of the falling object itself, the crossing would happen in finite time, and once across, there would be no return. The boundary was not a physical surface, not a wall or membrane that could be touched or felt, but rather a point of no return defined purely by the geometry of space-time. This boundary needed a name, something to capture its essential character as the threshold beyond which events could no longer influence the outside universe. The term that would eventually become standard was coined by a physicist named Wolfgang Rindler in 1956. Rindler was born in Vienna and had immigrated to Britain as a child, eventually becoming a professor at Cornell University in the United States. In a paper on relativistic cosmology, he introduced the phrase event horizon to describe boundaries in space-time beyond which events cannot communicate with distant observers. The term is apt and evocative, suggesting a horizon in the everyday sense, the line beyond which we cannot see, but applied to events in time as well as positions in space. Once something crosses the event horizon, it passes beyond the horizon of our experience, beyond the reach of any observation or signal or influence from outside. Throughout these decades, from the 1920s through the 1950s, the objects described by Schwarzschild's solution remained mathematical curiosities, fascinating to theorists, but not considered to be features of the actual universe. They were numbers on paper, dreams of geometry, possibilities permitted by the equations, but dismissed as physically implausible. No one had observed anything in the heavens that seemed to correspond to these strange predictions, and the mechanisms by which such objects might form remained unclear. Physicists knew how to write down the equations describing a region of space-time with such extreme curvature, but they could not imagine how nature might produce such conditions in practice. And so the Schwarzschild radius and the event horizon waited, patient and quiet, for the world to catch up with the mathematics. They were ideas ahead of their time, theoretical shadows cast by equations whose full meaning would only become clear decades later, when new observations and new theoretical insights would converge to suggest that these mathematical curiosities might, after all, be real. The universe, it would turn out, was stranger and more various than even the physicists of the early 20th century had imagined, and the dark companions of gravity that Michel and Laplace and Schwarzschild had glimpsed in their calculations were waiting out there in the cosmos, silent and invisible, for us to find them. But that discovery lay in the future, and for now, in the years between the wars and into the middle of the century. Black holes remained theoretical possibilities, notes in the margins of physics, beautiful mathematics without confirmed existence. In the summer of 1930, a young man named Subramanian Chandrasekhar boarded a steamship in Bombay, bound for England and the University of Cambridge, where he had been awarded a scholarship to study physics. He was 19 years old, and the voyage would take several weeks, passing through the Arabian Sea and the Suez Canal, across the Mediterranean, and eventually to the grey shores of Britain. It was a long journey, as ocean crossings in that era tended to be, and Chandrasekhar, finding himself with considerable time and very little to do, decided to occupy his days with calculations. He had brought with him some recent papers on the physics of stars, and he sat on the deck of the ship, or perhaps in his small cabin when the weather grew too warm, working through equations in his notebook, thinking about what happens to a star when it dies. What he discovered, somewhere between India and England, would eventually reshape our understanding of the universe, though it would take decades for the world to fully appreciate what this young man had found. Chandrasekhar was thinking about white dwarfs, those dense stellar remnants that we discussed earlier, and he was applying the new physics of quantum mechanics to understand their structure. The accepted wisdom at the time held that any star, regardless of its original size, could eventually settle into a peaceful retirement as a white dwarf, shrinking down to roughly the size of Earth and then remaining stable forever, slowly cooling over billions of years like an ember in a dying fire. It was a comforting picture, suggesting that stellar death was always a gentle process, a quiet fading rather than anything more dramatic. But Chandrasekhar, working through the mathematics with careful precision, found something troubling. When he applied the principles of special relativity to the electrons inside a white dwarf, he discovered that there was a limit, a maximum mass above which a white dwarf could not exist. If the stellar remnant contained more than about 1.4 times the mass of our Sun, the electron degeneracy pressure that holds a white dwarf up against gravity would simply not be strong enough. The electrons, pushed to ever higher speeds by the enormous compression, would approach the speed of light, and at that point the quantum mechanical support would falter, would prove insufficient against the relentless inward pull of gravity. There would be nothing to stop the collapse. This number, 1.4 solar masses, is now called the Chandrasekhar limit, and it represents one of the fundamental boundaries in astrophysics, a line in the cosmic sand that determines whether a dead star can rest peacefully or must face a more dramatic fate. But when Chandrasekhar arrived in Cambridge and began sharing his findings, the reception was far from welcoming. The most prominent astrophysicist in Britain at the time was Sir Arthur Eddington, the same Eddington who had confirmed Einstein's general relativity during the solar eclipse of 1919. A man of enormous prestige and influence in the scientific community. Eddington had his own ideas about stellar structure, and he did not care for what this young Indian student was suggesting. In January of 1935, at a meeting of the Royal Astronomical Society in London, Chandrasekhar presented his work to an audience of his peers, explaining carefully how relativity imposed this upper limit on white dwarf masses. When he finished, Eddington rose to speak, and what followed was not the collegial scientific discussion one might hope for. Eddington dismissed Chandrasekhar's conclusions entirely, declaring that there was no such limit, that stars would always find some way to avoid such a fate, that nature would not permit the kind of endless collapse that Chandrasekhar's mathematics implied. He did not point to errors in the calculations, because there were none, but rather argued on philosophical grounds that the result was simply unacceptable, that the universe could not possibly work this way. It was a difficult moment for a young scientist. To have his careful work publicly rejected by the most famous astronomer in the country, and the effects lingered for years. Many other physicists were reluctant to contradict Eddington, and Chandrasekhar eventually left the field of stellar structure entirely, turning his considerable talents to other areas of physics. He would go on to have a distinguished career, winning the Nobel Prize in Physics in 1983, partly for this very work that Eddington had so confidently dismissed half a century earlier. But in the 1930s, the question of what happens to massive stars when they die remained unresolved, at least in the minds of many astronomers. Meanwhile, other scientists were beginning to explore even more exotic possibilities. In 1932, the physicist James Chadwick had discovered the neutron, a subatomic particle with no electric charge that sits alongside protons in the nucleus of atoms. This discovery opened new avenues of thought about dense matter, and in 1934, just 2 years later, two astronomers working at the California Institute of Technology proposed something remarkable. Walter Baade and Fritz Zwicky, studying the phenomenon of supernovae, those tremendous stellar explosions that briefly outshine entire galaxies, suggested that such explosions might create a new type of object, something they called a neutron star. The idea was startling in its implications. Baade and Zwicky proposed that when a massive star exhausts its nuclear fuel and its core collapses, the tremendous pressures involved might squeeze matter to such extreme densities that electrons and protons would be forced to combine, forming neutrons. The result would be a star composed almost entirely of neutrons, packed together as tightly as the particles in an atomic nucleus, with densities so high that a single teaspoon of neutron star material would weigh several billion tons. Such an object would be extraordinarily small by stellar standards, perhaps only 10 or 20 kilometers across, yet it would contain more mass than our entire Sun. It was a theoretical prediction, and for more than 3 decades, neutron stars remained exactly that, theoretical. There was no observational evidence that such objects actually existed, and some astronomers doubted they ever would be found. The universe is large and dark, and a neutron star, being so incredibly small and potentially quite dim, seemed like it might be impossible to detect, a mathematical curiosity that nature might or might not have actually produced. Then, in the summer of 1967, A graduate student at Cambridge named Jocelyn Bell Burnell was reviewing data from a new radio telescope, a sprawling array of wires and poles spread across a field in the English countryside, designed to study the twinkling of distant radio sources. Bell Burnell noticed something strange in her recordings: a regular pulsing signal that repeated every 1.33 seconds with remarkable precision. At first, she and her supervisor, Anthony Hewish, were not sure what to make of it. The regularity of the signal was almost too perfect, more like a beacon than any natural phenomenon they could imagine. For a time, partly in jest but also partly in genuine puzzlement, they referred to the source as LGM-1, where LGM stood for Little Green Men. The precision of the pulses seemed almost artificial, as if some distant civilization might be broadcasting a signal across the void of space. But as weeks passed and more sources were discovered, all showing similar behavior but with different periods, it became clear that this was not alien communication, but rather something entirely new in astronomy. These were natural objects, whatever they were, and they were producing radio pulses with the regularity of the most accurate clocks on Earth. The explanation, when it came, connected beautifully to the predictions that Bardet and Zwicky had made more than 30 years earlier. These pulsing radio sources, soon called pulsars, were spinning neutron stars. When a massive star collapses to form a neutron star, conservation of angular momentum causes it to spin extremely rapidly, just as an ice skater spins faster when pulling in their arms. A star that once rotated leisurely over the course of weeks or months might, when compressed to a diameter of just 20 kilometers, spin several times per second, or in some cases hundreds of times per second. These spinning neutron stars often have intense magnetic fields, and as they rotate, beams of radio waves sweep through space like the beam of a lighthouse. When one of these beams happens to sweep across Earth, we detect a brief pulse of radio emission, and as the star continues to spin, the beam comes around again, producing another pulse, and another, with clockwork regularity. The pulsars that Bell Burnell discovered were not alien signals, but the spinning remnants of dead stars. The neutron stars that theory had predicted should exist. It was a beautiful confirmation of theoretical physics by careful observation, and it opened an entirely new field of study in astronomy. But if white dwarfs have an upper mass limit, one naturally wonders whether the same might be true of neutron stars. And indeed, it is. In the late 1930s, around the same time that Chandrasekhar's work was being unfairly dismissed, other physicists were beginning to explore this question. Richard Tolman at Caltech, along with Robert Oppenheimer and his student George Volkoff at Berkeley, worked out the equations governing the structure of neutron stars and found that they too have a maximum mass, a point beyond which even the incredible pressure of degenerate neutrons cannot hold back the force of gravity. This limit is now called the Tolman-Oppenheimer-Volkoff limit, and while its exact value depends on details of nuclear physics that are still not perfectly understood, it lies somewhere in the range of 2 to 3 solar masses. A neutron star can contain perhaps twice the mass of our Sun, compressed into a sphere no wider than a large city. But if you try to add more mass, the structure becomes unstable. The neutrons cannot push back hard enough. The core cannot support itself, and something else must happen. In 1939, Robert Oppenheimer, who would later become famous for his role in the Manhattan Project, published a paper with his student Hartland Snyder that explored what this something else might be. They took Einstein's equations of general relativity and applied them to a star that had exhausted all possibilities for support. A star massive enough that neither electron degeneracy pressure nor neutron degeneracy pressure could prevent its collapse. What they found was remarkable and, to many physicists of the time, deeply unsettling. According to their calculations, such a star would simply keep collapsing, falling inward without limit, the matter compressing to higher and higher densities as space and time themselves curved more and more sharply around the shrinking mass. From the perspective of an outside observer, watching from a safe distance, the collapsing star would appear to slow down as it approached a certain critical radius, its light growing ever dimmer and more redshifted, until it seemed to freeze at the edge of invisibility, fading from view without ever quite disappearing. But from the perspective of the collapsing matter itself, there would be no pause, no hesitation, just continuous inward fall toward a destiny that the mathematics could describe but the human mind could scarcely comprehend. This was a strange prediction, and many physicists preferred not to think about it too carefully. Surely something would intervene, some new physics not yet discovered, some mechanism that would halt the collapse before things became too extreme. The idea of matter falling forever inward, of space curving so sharply that nothing could escape, of time itself behaving in ways that defied ordinary intuition. All of this seemed too strange to be real. And so, for nearly 3 decades, the prediction languished in obscurity, occasionally discussed but rarely taken seriously as a description of actual objects that might exist in the universe. Then, in 1967, the same year that Jocelyn Bell Burnell discovered pulsars, the American physicist John Wheeler was giving a lecture at a conference in New York. Wheeler had been thinking about these collapsed objects, trying to understand their properties and their implications, and he needed a name for them. The technical terminology that had been used previously was cumbersome and failed to capture the imagination. As Wheeler spoke, someone in the audience suggested a simpler term, and Wheeler liked it well enough to adopt it for his lecture and his subsequent writings. The name was black hole. It was a vivid phrase, conjuring images of emptiness and darkness, of a region in space where something has been removed, where matter has fallen in and light cannot get out. The name caught on quickly, spreading through the physics community and eventually into popular culture, becoming one of the most evocative terms in all of science. And with the name came renewed interest in the physics, a recognition that these objects, whether or not they actually existed in nature, deserved serious theoretical attention. The era of black hole physics had begun in earnest, and the universe, it would turn out, had been creating these objects all along, waiting patiently for us to understand what we were looking for. And now we come to a rather gentle puzzle, one that astronomers have considered for many decades, which is simply this: how does one go about observing something that produces no light of its own, something that holds on to every photon that ventures too close? something that by its very nature refuses to announce itself in the usual manner of stars and galaxies and all the luminous furniture of the cosmos. It is a reasonable question to ask, and the answer, as it turns out, is rather comforting in its simplicity. Because, while a black hole itself may be invisible, it is not silent, and it is certainly not without influence. And so we learn to watch for the effects it has on everything around it. The gentle disturbances it creates in the fabric of space and time. The way it tugs at passing matter and bends the light of distant stars. And through these indirect whispers, these second-hand clues, we come to know that something is there, even when we cannot see it directly. This method of detection through influence is not unique to astronomy, of course, and you may find it soothing to consider that we use similar reasoning in everyday life, noticing the presence of a breeze by the movement of leaves rather than by seeing the air itself, or knowing that someone has walked through a room by the lingering warmth of their footsteps on a cold floor. And in much the same way, astronomers have learned to read the signs that black holes leave behind, the gravitational signatures written in the motion of nearby stars, the heating of gas as it spirals inward, the bending of light from more distant sources, all of these adding up to a portrait of something massive and compact and utterly dark, something that must be there even though it cannot be photographed in the conventional sense. One of the earliest and most compelling pieces of evidence for the existence of black holes came from a region of sky in the constellation Cygnus, which is named for the swan and which traces a graceful cross of stars through the northern summer sky. And it was here, in the year 1964, that a most interesting discovery was made, not by a telescope on the ground, but by instruments carried aloft on a rocket. Brief flights that lasted only minutes, but which opened a new window onto the universe by detecting X-rays, a form of light far more energetic than what our eyes can see, and which cannot penetrate the Earth's atmosphere, meaning that to observe it, we must send our detectors above the blanket of air that protects us. During one of these rocket flights, astronomers detected a powerful source of X-rays coming from Cygnus, and they gave it the name Cygnus X1, the X standing for X-ray and the 1 indicating it was the first such source catalogued in that constellation. And this object would go on to become perhaps the most famous black hole candidate in all of astronomy, a touchstone for decades of research and debate. What made Cygnus X1 so compelling was not merely that it produced X-rays, though that was certainly intriguing, but rather what subsequent observations revealed about the nature of the system, because when astronomers turned their optical telescopes towards this region, they found a star, a blue supergiant known by the catalogue designation HDE 2268618 which is a rather long name but simply reflects the systematic way astronomers label the countless stars in the sky. And this star was enormous, many times the mass of our own sun, and blazing with a brilliant blue-white light, the kind of star that burns through its fuel quickly and lives a relatively short but spectacular life. But here was the curious thing. This blue supergiant was not alone, and careful measurements of its light revealed that it was wobbling, shifting back and forth in a telltale rhythm that indicated it was being tugged by the gravity of a companion, something massive orbiting around their common center of mass. And yet, when astronomers looked for this companion, they could see nothing. Only the empty darkness of space beside the brilliant blue star. This invisible companion, whatever it was, had to be extraordinarily massive to exert such a strong gravitational pull on the supergiant. And when astronomers calculated the numbers, they found that it contained perhaps 10 times the mass of our Sun or more, all compressed into a region so small that it could not be seen directly. And there were really only a few possibilities for what such an object could be. It might have been another star, but if so, it should have been visible, and extensive searches found nothing. It might have been a neutron star, one of those incredibly dense remnants left behind when a massive star explodes. But neutron stars have an upper limit to their mass, and this invisible companion seemed to exceed that limit by a comfortable margin. And so, by process of elimination, astronomers began to suspect that they were looking at something even more exotic, a black hole, an object whose gravity was so intense that not even light could escape, which would explain perfectly why it could be so massive and yet remain utterly invisible. The case for Cygnus X1 being a black hole was strong enough to provoke a rather famous wager between two of the most prominent physicists of the 20th century, Stephen Hawking and Kip Thorne, who in 1974 made a bet about the nature of this mysterious object. Hawking, with his characteristic contrarian wit, bet against Cygnus X1 being a black hole, not because he doubted the existence of black holes in general, but perhaps because he understood the importance of skepticism in science and wanted to hedge against the possibility that some other explanation might eventually emerge. Thorne, for his part, bet that the evidence would ultimately confirm the black hole interpretation. The stakes were a subscription to a magazine of the winner's choosing. And for 16 years, the bet remained unresolved. As astronomers gathered more and more data about this enigmatic system, finally, in 1990, Hawking conceded the bet, acknowledging that the evidence had become overwhelming and that Cygnus X1 was indeed almost certainly a black hole. And by all accounts, he did so with good humor, having always understood that being wrong is simply part of the scientific process. The X-rays that first drew attention to Cygnus X1 require a moment of gentle explanation, because they tell us something important about how matter behaves near a black hole, and the story is rather elegant in its physics. When gas from the blue supergiant is pulled toward the black hole by gravity, it does not fall straight in, at least not usually, because any small sideways motion gets amplified as the gas spirals closer, much like water circling a drain, and this creates what astronomers call an accretion disk, a flattened swirl of material orbiting the black hole at tremendous speed. As this gas spirals inward, it becomes compressed and heated by friction and other processes, reaching temperatures of millions of degrees, far hotter than the surface of any star, and matter at such extreme temperatures emits radiation not in the gentle visible light we see with our eyes, but in the far more energetic form of X-rays. So, the X-rays we detect from Cygnus X1 and similar systems are not coming from the black hole itself, which emits nothing, but from the superheated material just outside the event horizon, the last desperate glow of matter about to disappear forever. And this is how we see the unseeable, by watching the light of what is about to be consumed. The detection of cosmic X-rays was greatly advanced by a satellite launched in 1970 from a platform off the coast of Kenya, an appropriate location because Kenya lies on the equator, which provides certain advantages for launching rockets into orbit. This satellite was given the name Uhuru, which means freedom in Swahili, and it was launched on the 12th of December, the 7th anniversary of Kenyan independence, a small gesture toward the universality of scientific exploration and the hope that the cosmos might belong to all of humanity. Uhuru was the first satellite dedicated entirely to X-ray astronomy, and over its operational lifetime, it catalogued hundreds of X-ray sources scattered across the sky, revealing a universe far more violent and energetic than what our eyes alone could perceive. And among its many discoveries were further observations of Cygnus X1 and other systems that would eventually be recognized as black hole candidates. The data from Uhuru helped establish X-ray astronomy as a legitimate field and paved the way for subsequent missions that would map the X-ray sky in ever greater detail. There is another way to detect the presence of a black hole, one that relies not on the light emitted by infalling matter, but on the distortion of light from more distant sources. And this phenomenon is called gravitational lensing, a direct consequence of Einstein's general theory of relativity, which tells us that massive objects bend the fabric of spacetime, and that light follows this curved geometry as it travels through the universe. When light from a distant star or galaxy passes near a massive object, such as a black hole, its path is deflected, bent inward by the gravitational influence, and if the alignment is just right, this bending can produce multiple images of the same background source, or arcs and rings of distorted light, or a subtle brightening as rays that would otherwise have missed us are focused toward our telescopes. By studying these gravitational lensing effects, astronomers can infer the presence and mass of objects that might otherwise be invisible, mapping the distribution of matter in the universe through its influence on passing light. For isolated black holes drifting through space, those not part of a binary system with a bright companion star, gravitational lensing offers one of the few ways to detect their presence. Because without a source of infalling gas, they produce no X-rays, and without a visible companion star, there is no wobbling to observe. And so they would remain entirely hidden were it not for the occasional fortuitous alignment that allows them to act as a gravitational lens. These events are rare and brief, lasting weeks or months as the black hole drifts across our line of sight to a more distant star. But modern surveys that monitor millions of stars continuously have begun to detect such events, adding to our census of dark objects wandering through the galaxy. By the 1990s, several decades after the discovery of Cygnus X1, the evidence for stellar mass black holes had grown considerably, with dozens of candidates identified through various indirect methods: X-ray emissions from accretion disks, the orbital motion of visible companion stars, gravitational lensing events, and other subtle signatures, each adding another piece to the puzzle. None of these detections involved seeing the black hole directly, which remained as invisible as ever. But the cumulative weight of evidence became difficult to deny, and the scientific consensus shifted toward acceptance that these objects were real, that Einstein's equations had predicted something true about the universe, and that scattered throughout the cosmos were these remarkable endpoints of stellar evolution, dark and silent and enormously massive, detectable only through their influence on the matter and light around them. It is rather reassuring, In a way, to know that the universe reveals its secrets through these gentle clues, that even the most extreme and invisible objects leave traces for patient observers to find. Whispers in the motion of stars and the heating of gas and the bending of distant light, and that with careful observation and thoughtful analysis we can come to understand things that might seem forever beyond our reach. The story of how we learnt to see black holes is a story of ingenuity and persistence, of rockets and satellites and telescopes spanning the electromagnetic spectrum, of bets between friends and the slow accumulation of evidence over decades. And it reminds us that the universe, however strange and dark it may sometimes appear, is not entirely opaque to those who know how to listen. And now we come to something rather vast and rather quiet, which seems a fitting combination for this time of night. And that is the subject of the enormous black holes that sit at the centers of galaxies, including our own, where they have been residing for billions of years in a kind of patient stillness that belies their tremendous mass. These are called supermassive black holes. And the name is quite straightforward, really, because they are simply black holes of a size that makes the stellar mass black holes we discussed earlier seem almost modest by comparison, with masses ranging from several million times that of our Sun all the way up to several billion times that of our Sun, which is a range so large that it takes a moment to settle into the mind. And there is no need to rush that settling, as we have plenty of time here in the dark. The story of how we came to understand that such enormous objects exist begins, as many astronomical stories do, with light arriving from a great distance and presenting a puzzle that took some years to unravel. And in this case, the light came from objects that were first noticed in the late 1950s and early 1960s by radio astronomers who were surveying the sky and finding sources of radio waves that seemed, when they looked through optical telescopes, to be associated with what appeared to be rather ordinary-looking stars. These sources were given the name quasi-stellar radio sources, which was soon shortened to quasars, and they were puzzling because their spectra, which is to say, the patterns of light they emitted at different wavelengths, did not match anything that astronomers expected to see from stars, and the patterns seemed shifted in ways that did not immediately make sense. It was in 1963 that an astronomer named Martin Schmidt, working at the Palomar Observatory in California, was studying one of these quasars, designated 3C273 because it was the 273rd object in the third Cambridge catalogue of radio sources, and he had been puzzling over its spectrum for some time, trying to understand why the emission lines appeared at wavelengths that did not correspond to any known elements. And then Schmidt realized something that changed our understanding of the universe rather dramatically, though in the quiet way that scientific realizations often occur, which is to say, he was sitting at his desk and the numbers suddenly made sense. And what he realized was that the spectrum did show the familiar pattern of hydrogen emission, but it had been shifted so dramatically toward the red end of the spectrum that the wavelengths had moved by about 16%. This redshift, as it is called, is caused by the expansion of the universe stretching the light as it travels through space. And the amount of stretching tells us how far away the source is and how fast it is receding from us. And when Schmidt calculated what a 16% redshift meant, he found that 3C273 must be about 2.5 billion light-years away, which was a staggering distance for an object that appeared so bright in the sky. For something to be that far away and yet shine so brilliantly meant that it must be producing an almost unimaginable amount of energy, more than 100 times the light output of our entire Milky Way galaxy with its hundreds of billions of stars. And yet, this light was coming from a region so compact that variations in its brightness over periods of days suggested the source could be no larger than our solar system. The only mechanism that physicists could propose to explain such concentrated power was matter falling into an extremely massive black hole, heated to incandescent temperatures as it spiraled inward. And so it gradually became clear that quasars were not stars at all, but rather the brilliant beacons of supermassive black holes in the act of consuming material at tremendous rates. The matter falling towards these black holes forms a swirling disk, heated by friction and compression to temperatures of millions of degrees. And this disk, called an accretion disk, glows so fiercely that it can outshine the entire galaxy surrounding it, which is why early observers saw what looked like a single point of light rather than a collection of billions of stars. This was quite a lot to absorb in 1963, and the decades that followed brought further discoveries that confirmed and extended this picture, as astronomers found quasars at ever greater distances, some so far away that their light had been traveling for more than 13 billion years, which meant they existed when the universe was less than 1 billion years old. But knowing that quasars were powered by distant supermassive black holes left another question hanging in the astronomical air, which was whether such black holes existed closer to home, perhaps even at the center of our own galaxy, where they might be observable in a more direct fashion. The center of the Milky Way lies in the direction of the constellation Sagittarius, about 26,000 light-years from where we sit, and it is hidden from optical telescopes by vast clouds of dust that absorb visible light. But infrared and radio waves can pass through this dust. And so astronomers have been able to study the galactic center using these longer wavelengths. In the 1970s and 80s, radio observations revealed a compact and unusual source of radio emission at the very center of the galaxy, which was given the name Sagittarius A star, with the star part being a notation indicating that it was a particularly compact source. And there was speculation that this might be a massive black hole, but proving it required evidence that was difficult to obtain. The evidence came from 2 research groups working independently over many years, one led by Andrea Ghez at the University of California, Los Angeles, and the other led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany. And both groups undertook the painstaking work of tracking the motions of stars near the galactic center over periods measured in decades. This was challenging observational work because even though the galactic center appears to us as a crowded field of stars, individual stars near the central black hole are difficult to distinguish from one another, and measuring their positions accurately requires correcting for the blurring effects of Earth's atmosphere, which both groups accomplished using a technique called adaptive optics that adjusts telescope mirrors hundreds of times per second to compensate for atmospheric distortion, year after year. Both teams took measurements and plotted the positions of stars, building up records of their orbits the way one might trace the path of a slow-moving insect across a window. Except that each measurement required sophisticated equipment and careful analysis. And the stars were not insects, but massive suns racing through space at tremendous velocities. One star in particular proved especially valuable for understanding the mass at the center. And this was a star designated S2, which follows a highly elongated elliptical orbit that brings it, at closest approach, to within about 17 light-hours of Sagittarius A star, which is roughly 4 times the distance from the Sun to Neptune. The orbital period of S2 is about 16 years, which meant that Ghez and Genzel and their teams had to observe patiently for many years to see even a single complete orbit. But this patience was rewarded with extremely precise measurements of the star's path. At its closest approach to the central object, S2 moves at velocities of about 7,650 kilometers per second, which is about 2.5% of the speed of light, a remarkable velocity for a star, and the shape and speed of its orbit allowed astronomers to calculate the mass of the object it was orbiting with considerable precision. The answer that emerged from these decades of careful observation was that the central object, Sagittarius A star, has a mass of about 4 million times the mass of our Sun, packed into a region no larger than would fit comfortably within the orbit of Mercury around our own Sun, and there is no known form of matter other than a black hole that could concentrate such tremendous mass into such a compact space. This work, spanning more than 25 years of observations and involving contributions from many researchers in addition to the 2 principal investigators, was recognized with the Nobel Prize in Physics in 2020, which Andrea Ghez and Reinhard Genzel shared with Roger Penrose, who, as we mentioned earlier, had done foundational theoretical work on black holes some decades before. There is something rather calming about the way this discovery was made, through patient accumulation of evidence over years and decades, watching stars trace out their orbits the way one might watch clouds drift across the sky on a lazy afternoon. Except that the timescale was longer and the stakes were the confirmation of an extraordinary object at the heart of our galaxy. And our Milky Way, it turns out, is not unusual in this regard, as observations of other galaxies over the past several decades have revealed that nearly every large galaxy appears to host a supermassive black hole at its center, as though this were simply part of the standard architecture of galaxies rather than a rare peculiarity. The masses of these central black holes vary considerably from galaxy to galaxy, and there appears to be a relationship between the mass of the central black hole and the properties of its host galaxy, with larger galaxies tending to have larger central black holes, though the black hole itself is typically only a small fraction of a percent of the total mass of stars in the galaxy. One of the most impressive examples of a supermassive black hole is found at the center of the giant elliptical galaxy M87, which is located about 55 million light-years away in the constellation Virgo, and which hosts a black hole with a mass of about 6.5 billion times that of our Sun. This is more than 1,000 times more massive than Sagittarius A star, and it powers a jet of material that shoots outward from the galactic center for thousands of light-years, visible in telescopes as a thin, bright streak emerging from the galaxy's core, which is the result of matter being accelerated to nearly the speed of light by processes occurring very close to the black hole. The M87 black hole became famous in 2019 when the Event Horizon Telescope collaboration released the first image of a black hole's shadow, showing a ring of bright emission surrounding a dark central region. But that is perhaps a topic for another time. And for now, we may simply note that this image confirmed what decades of indirect evidence had suggested, that these massive objects are indeed present at the centers of galaxies. What remains gently mysterious, in the way that good mysteries are, is how these supermassive black holes came to be. Because, as we mentioned when discussing stellar mass black holes, the collapse of a single star can produce a black hole of perhaps a few tens of solar masses at most, which is a very long way from the millions or billions of solar masses found in supermassive black holes. One might suppose that black holes simply grow over time by consuming nearby matter, and indeed they do grow in this fashion. But the difficulty is that observations of very distant quasars show that supermassive black holes already existed when the universe was less than 1 billion years old, which does not seem like enough time to grow from a small seed to a giant. There are several possible explanations that astronomers are currently investigating, including the idea that some black holes may have formed directly from the collapse of enormous primordial gas clouds in the early universe, bypassing the stellar stage entirely and producing what are called direct collapse black holes with masses of tens of thousands or even hundreds of thousands of solar masses right from the beginning. Another possibility is that black holes in the early universe were able to grow more rapidly than simple calculations suggest, perhaps by consuming matter at rates that exceed the usual limits, or by merging frequently with other black holes in the crowded conditions of the young universe. These questions remain open, and astronomers continue to search for the earliest supermassive black holes, looking back in time by observing the most distant quasars, trying to understand how these giants arose so quickly in the youth of the cosmos. But there is no urgency to solve these puzzles tonight, and they will still be there tomorrow, and next year, and the supermassive black hole at the center of our own galaxy will continue to sit quietly in its place, not currently feeding on any significant amount of material and therefore not shining as a quasar, just a dark, massive presence around which stars orbit in their patient paths. The star S2 is out there right now, tracing its 16-year ellipse, moving through the dark at thousands of kilometers per second, and yet, from our perspective, it barely seems to move at all. And astronomers will continue to watch it and other stars, refining their measurements and learning more about the object they orbit. And perhaps there is something restful in the thought of these enormous objects sitting quietly at the hearts of galaxies, including our own, part of the deep structure of the universe, formed in processes we are still working to understand, present since near the beginning of cosmic time, and likely to remain for eons yet to come. The universe is full of such large and patient things, and we are small and brief by comparison, but we have the pleasant ability to think about them as we drift toward sleep, and to find them interesting without needing to feel any concern about them, because they are very far away and very quiet, and the night is calm, and there is always more to learn tomorrow. Sometimes the most profound achievements in science arrive not with a sudden flash of insight, but through years of quiet coordination, the patient accumulation of data, and the steady collaboration of hundreds of people working across vast distances toward a single shared goal. The first photograph of a black hole is one such achievement, and the story of how it came to be is a gentle reminder that even the most exotic objects in our universe can be studied, measured, and eventually seen, if only we are willing to build the right instruments and wait for the right moment. To photograph a black hole is, in some ways, a contradiction. A black hole itself emits no light, and so it cannot be seen directly. What can be seen, however, is the material that surrounds it, the superheated gas and dust that swirl inward, glowing brightly as they are compressed and accelerated to tremendous speeds. This glowing ring of material, caught in the gravitational grip of the black hole, outlines the darkness at the center, much as the glow of a street lamp on a foggy night reveals the shape of the mist around it. The shadow at the center of that ring is the black hole's silhouette, the region where light has been swallowed or bent so severely that it cannot reach us. To capture this shadow, astronomers needed a telescope unlike any that had existed before, one with a resolution fine enough to see a ring of fire smaller than a grain of sand held at arm's length, located more than 50 million light-years away. No single telescope on Earth could achieve such a feat. The laws of optics tell us that the resolving power of a telescope depends on its size, and to see something so small and so distant would require a dish as wide as our entire planet. Building such a dish is, of course, impossible, but there is a way to achieve something very close to the same result. By linking together many smaller telescopes spread across the globe, each one recording the same signals from the same distant source, astronomers can combine their data to create what is known as a virtual telescope, one whose effective diameter is equal to the greatest distance between any two of its component dishes. This technique is called very long baseline interferometry, and it is the foundation upon which the Event Horizon Telescope was built. The Event Horizon Telescope is not a single instrument, but a collaboration, a network of 8 radio observatories scattered across 4 continents and numerous islands, from the frozen plains of Antarctica to the volcanic slopes of Hawaii, from the high deserts of Chile to the mountains of Spain. Each of these observatories contributed its own data to the project, and together they formed a virtual dish spanning nearly the entire diameter of the Earth. The observatories involved include the Atacama Large Millimeter Array in Chile, the South Pole Telescope in Antarctica, the IRM 30-meter telescope on Pico Veleta in Spain, the James Clerk Maxwell Telescope and the Submillimeter Array in Hawaii, the Large Millimeter Telescope in Mexico, the Submillimeter Telescope in Arizona, and the Apex Telescope, also in Chile. Each of these instruments was carefully prepared and coordinated so that, during the observing window, they would all point toward the same target and record the incoming radio waves with extraordinary precision. At the heart of this coordination was a man named Shepard Dullman, an astronomer at the Harvard-Smithsonian Center for Astrophysics who had spent much of his career working toward the goal of imaging a black hole. Dullman served as the founding director of the Event Horizon Telescope project, guiding the collaboration through years of planning, testing, and refinement. Under his leadership, the team grew to include more than 300 scientists and engineers from institutions around the world. each contributing their expertise to the enormous technical challenges involved. The goal was ambitious but clearly defined: to capture the shadow of a supermassive black hole and, in doing so, to test the predictions of general relativity in the most extreme environment imaginable. The observations themselves took place in April of 2017, during a brief window when weather conditions were favorable at most of the participating sites. For several nights, the telescopes recorded radio waves at a wavelength of 1.3 millimeters, a frequency chosen because it can penetrate the clouds of gas and dust that surround the target black holes, allowing the glow of the innermost material to reach us. Each telescope recorded the incoming signals onto banks of hard drives, capturing enormous quantities of data at rates of tens of gigabits per second. The synchronization of these recordings was achieved through the use of hydrogen maser atomic clocks, instruments so precise that they lose less than a second over millions of years. These clocks allowed the data from each telescope to be time-stamped with exquisite accuracy, a necessity for the later process of combining the recordings into a single coherent image. When the observations were complete, the hard drives were collected and shipped by airplane to central processing facilities at the MIT Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Germany. One might wonder why the data was not simply transmitted over the internet, and the answer is a matter of sheer volume. The total amount of data collected during the observing run amounted to several petabytes, a quantity so vast that sending it electronically would have taken far longer than simply loading the hard drives onto planes and flying them to their destinations. In this way, the most advanced imaging project in the history of astronomy relied, at a crucial stage, on one of the oldest methods of data transfer: the physical movement of storage media from one place to another. The process of turning those petabytes of raw data into an image was itself a monumental task. The technique of very long baseline interferometry does not produce a photograph in the usual sense. Instead, it produces a collection of measurements that describe how the brightness of the source varies across different scales and orientations. To reconstruct an image from these measurements, sophisticated algorithms are required, and one of the most important contributions to this effort came from a young computer scientist named Katie Bauman. While still a graduate student at the Massachusetts Institute of Technology, Bauman developed an algorithm called CHIRP, which stands for Continuous High-Resolution Image Reconstruction using patch priors. This algorithm, along with several others developed by the collaboration, allowed the team to piece together a reliable image from incomplete data, filling in the gaps left by the finite number of telescopes and the limited coverage of the Earth's surface. Bauman's work was part of a larger effort involving multiple independent teams, each using different methods to reconstruct the image. By comparing the results of these different approaches, the collaboration could be confident that the final image was not an artifact of any one algorithm, but a true representation of the data. The care and rigor with which this process was carried out reflects the scientific community's commitment to accuracy and transparency, a quiet dedication that often goes unnoticed but is essential to the integrity of any discovery. On the 10th of April in 2019, the results were announced simultaneously at press conferences held in 6 cities around the world. The image revealed that day showed a glowing ring of orange and yellow light, slightly brighter on one side than the other, surrounding a dark central region. The ring was the superheated gas orbiting the supermassive black hole at the center of Messier 87, a giant elliptical galaxy located in the constellation Virgo, some 55 million light-years from Earth. The dark shadow at the center was the silhouette of the black hole itself, a region roughly 40 billion kilometers across, larger than our entire solar system. The slight asymmetry in the brightness of the ring was due to the motion of the gas, which was approaching us on one side and receding on the other, causing the light to be boosted or diminished by relativistic effects. The image was met with quiet wonder by scientists and the public alike. It was not a dramatic explosion or a sudden revelation, but a gentle confirmation, a visual affirmation of ideas that had been discussed and debated for more than a century. The size and shape of the shadow matched the predictions of general relativity with remarkable precision, offering yet another piece of evidence that Einstein's theory describes the behavior of gravity even in the most extreme conditions. The mass of the black hole, inferred from the size of the shadow and the distance to M87, was estimated at roughly 6.5 billion times the mass of our Sun, a number so large that it is difficult to comprehend, but which fits comfortably within the framework of our existing understanding. 3 years later, in May of 2022, the Event Horizon Telescope collaboration released a second image, this time of the supermassive black hole at the center of our own galaxy, known as Sagittarius A star. This object is much closer to us, located only about 27,000 light-years away, but it presented its own unique challenges. Sagittarius A star is far less massive than the black hole in M87, containing only about 4 million solar masses, and as a result, the gas orbiting it moves much faster and changes on much shorter timescales. While the material around M87's black hole takes days or even weeks to complete an orbit, the gas around Sagittarius A star can circle the black hole in a matter of minutes. This rapid variability made it much harder to construct a stable image, as the source was constantly shifting and flickering during the observations. To overcome this difficulty, the team developed new techniques for averaging and combining the data, capturing the underlying structure of the ring even as its details changed from moment to moment. The resulting image showed a similar glowing ring surrounding a dark shadow, though the ring appeared somewhat more disordered and variable than that of M87. Once again, the size and shape of the shadow agreed with the predictions of general relativity, providing further confirmation that our understanding of black holes is correct. Even in environments where gravity is unimaginably strong and space-time is bent to its breaking point. It is worth pausing to appreciate what these images represent. A century ago, Einstein published his general theory of relativity, predicting that massive objects could warp the fabric of space-time and that, under certain conditions, this warping could become so extreme that nothing, not even light, could escape. The idea of a black hole was, for many years, considered a mathematical curiosity, a solution to the equations that might not correspond to anything real. Yet here, in the early decades of the 21st century, we have not only confirmed the existence of black holes, but have seen them with our own eyes. captured their shadows against the glow of infalling matter, and measured their properties with extraordinary precision. The Event Horizon Telescope continues its work, refining its techniques, adding new observatories to its network, and searching for ever more detailed views of these cosmic shadows. Future observations may reveal the motion of gas around the black holes, the structure of the magnetic fields that thread through the glowing rings, and perhaps even subtle deviations from the predictions of general relativity, hints of new physics waiting to be discovered. For now, the images stand as a testament to what can be achieved through patience, collaboration, and a willingness to pursue questions that seem, at first glance, unanswerable. And so, as you rest and let your thoughts drift, you might picture that glowing ring of light, steady and unchanging over the course of human lifetimes, circling a darkness so deep that it swallows everything that ventures too close. The shadow at the center is not empty, but simply hidden, a reminder that the universe holds mysteries that we are only beginning to glimpse, one careful observation at a time. And so we arrive at a place of gentle wondering, a place where even the most careful scientists must admit that not everything is known, and that some questions remain beautifully, peacefully open. This is perhaps the most restful part of our journey together, because here we can simply sit with mystery, allowing it to exist without needing to solve it, without urgency or demand. The universe has been patient for billions of years, and it will continue to be patient while we rest, while we drift, while we let our thoughts grow soft and slow like light bending around a distant star. Beyond the event horizon, past that gentle boundary where escape velocity exceeds the speed of light, there lies a realm that no telescope has ever seen, no instrument has ever measured, and no traveler has ever returned from to describe. What happens there, in that hidden interior, remains one of the most peaceful mysteries in all of physics. Peaceful because it asks nothing of us tonight, except perhaps a quiet moment of contemplation. The mathematics suggests that matter continues falling inward, that space-time curves more and more extremely, that at the very center there may exist what physicists call a singularity, a point of infinite density where our current understanding of physics simply and gracefully admits that it does not know how to proceed. Some theorists imagine that new physics must emerge there, that quantum gravity, a theory that would marry the very large and the very small, must take over and describe what happens in those final moments of collapse. But we do not yet have that theory complete, and so the singularity remains shrouded, hidden behind the event horizon like a small room with a closed door, quiet and private and patient. In 1974, a young physicist named Stephen Hawking was working on the mathematics of black holes when he discovered something that surprised everyone, including himself. He found that black holes are not entirely black after all, that they must emit a faint, incredibly faint glow of radiation. This came to be known as Hawking radiation, and it emerges from the strange quantum mechanical processes that occur at the very edge of the event horizon, where the vacuum of space itself becomes a gentle sea of fleeting particle pairs, appearing and disappearing in the tiniest fractions of moments. Occasionally, Hawking showed one particle of a pair might fall into the black hole while its partner escapes into space, carrying with it a tiny amount of energy that the black hole must pay for by losing an equally tiny amount of its mass. This process is extraordinarily slow, almost impossibly slow, occurring at a rate that makes geological time seem hurried by comparison. A stellar mass black hole, one formed from the collapse of a massive star and weighing perhaps 10 times as much as our Sun, would take approximately 10 to the power of 67 years to fully evaporate through this process. That number is so large that it becomes a kind of poetry rather than a quantity anyone could truly comprehend. 10 to the 67th power is a 1 followed by 67 zeros, a span of time that makes the current age of the universe, a mere 14 billion years, seem like less than a blink, less than the flutter of an eyelid, less than the time it takes for a single photon to cross an atom. And so, black holes, even as they slowly radiate away, will endure for timescales that we can only acknowledge with a kind of peaceful surrender, knowing that they will be here long after everything else we know has changed beyond recognition. But Hawking's discovery, beautiful as it was, brought with it a puzzle that physicists have contemplated for decades now, a puzzle that became known as the information paradox. In 1976, Hawking published a paper exploring this question more deeply, and what he found seemed to suggest something troubling about the nature of reality itself. When matter falls into a black hole, it carries with it information, the complete description of what that matter was, its quantum state, its history, everything that would be needed in principle to reconstruct it. But Hawking's calculations seemed to show that the radiation emitted by an evaporating black hole was purely thermal, purely random, carrying no trace of what had fallen in. This meant that when a black hole finally evaporated away completely, the information about everything it had ever consumed would simply be gone, erased from the universe entirely. This troubled physicists because the fundamental laws of quantum mechanics insist that information must be conserved, that nothing can truly be lost, only transformed or scrambled or hidden. The apparent conflict between Hawking's result and quantum mechanical principles became one of the deepest puzzles in theoretical physics, debated quietly in lecture halls and seminar rooms, contemplated over cups of tea and during long walks, considered with the kind of patient attention that the best questions deserve. Over the years, many possible resolutions have been proposed, each one offering a different way to think about what might really be happening when matter meets its fate at an event horizon. One of the most elegant ideas emerged from the work of Leonard Susskind and others in the 1990s. Building on earlier insights from Gerard 't Hooft, they developed something called the holographic principle, which suggests that all the information about what falls into a black hole might not be lost at all, but rather encoded on the event horizon itself, spread across that two-dimensional surface like writing on a spherical page. In this picture, the three-dimensional interior of a black hole might be something like a projection, a hologram created by the information stored on the boundary. If this is correct, then nothing is truly lost. The information merely waits there, patient and complete, eventually finding its way back out into the universe through subtle correlations in the Hawking radiation that were not visible in the original calculations. This idea, that a volume of space might be completely described by information on its boundary, has become one of the most profound and far-reaching concepts in modern theoretical physics, connecting black holes to quantum information theory and even to our understanding of how space-time itself might emerge from more fundamental quantum processes. But whether this resolution is the correct one, whether information truly is preserved in this way, remains a question that physicists continue to explore with care and thoughtfulness, knowing that the answer may reshape our understanding of reality itself. While theorists contemplated these deep questions, experimentalists were developing new ways to observe black holes directly, to catch them in the act of doing what black holes do. On September 14, 2015, something remarkable happened at two enormous facilities in the United States, one in Louisiana and one in Washington State, both part of an experiment called LIGO, the Laser Interferometer Gravitational Wave Observatory. At that moment, both detectors registered a distinctive signal, a brief chirp of gravitational waves that had traveled across the universe for over 1 billion years before reaching Earth. These waves were ripples in the fabric of space-time itself, produced by two black holes, one about 36 times the mass of the Sun and the other about 29 times, spiraling toward each other and finally merging into a single larger black hole about 62 times the mass of the Sun. The missing mass, about 3 times the mass of our Sun, had been converted entirely into gravitational wave energy during the final moments of the merger, radiating outward through the cosmos at the speed of light. Albert Einstein had predicted the existence of gravitational waves a century earlier, in 1916, as a consequence of his general theory of relativity, but he had doubted whether they would ever be detected, thinking them perhaps too faint to observe. The LIGO discovery, announced in February of 2016, proved that Einstein's mathematics had been right all along, and opened an entirely new way of observing the universe, a way of listening rather than looking, of feeling the gentle stretching and squeezing of space as these cosmic signals pass through us. Since that first detection, the field of gravitational wave astronomy has grown with quiet enthusiasm. More than 90 black hole mergers have now been observed, each one adding to our understanding of how these objects form, how they find each other across the vastness of space, and how they combine to create ever larger black holes. Some of these merging pairs have been roughly equal in mass, while others have been more lopsided, with one black hole significantly larger than its companion. Some mergers have occurred relatively nearby in cosmic terms, while others have sent their signals from billions of light-years away, from epochs when the universe was younger and different. Each detection is a small gift of information, a quiet message from distant corners of the cosmos, telling us something new about the population of black holes that drift through galaxies everywhere. Neutron star mergers have also been detected, and even the merging of a neutron star with a black hole, expanding the catalogue of cosmic collisions that we can now witness through this new sense, this gravitational hearing that Einstein's equations made possible. And so we come to rest with a contemplation, a gentle acknowledgement of what black holes truly are and what they mean in the grand tapestry of the universe. They are, in their way, cosmic recyclers, taking matter that has lived out its life in stars and planets and gas clouds, and drawing it inward, compacting it, transforming it into something new. The energy released as matter falls toward a black hole can outshine entire galaxies, powering the brightest objects in the universe. But eventually, all that matter settles beyond the event horizon, joining whatever mysterious state exists within over eons that stretch beyond comprehension. Perhaps even that matter will slowly return to the universe through the patient process of Hawking radiation, completing a cycle that spans timescales we cannot truly imagine. In this sense, black holes are not destroyers but transformers, not endings but slow and patient participants in the ongoing story of cosmic matter and energy. They are also sculptors of space-time, the most extreme examples of Einstein's vision of gravity as geometry. Around every black hole, space curves and time flows differently, creating a landscape of warped dimensions that light and matter must navigate according to rules utterly unlike those we experience in our everyday lives. The event horizon, the ergosphere, the innermost stable circular orbit. All of these are features carved into the fabric of reality by the presence of concentrated mass, regions where the ordinary intuitions of distance and duration no longer apply. In mapping these regions, in understanding their properties, physicists have learned profound things about the nature of space-time itself, insights that ripple outward into our understanding of cosmology and quantum gravity and the fundamental structure of existence. And yet, for all we have learned, black holes remain keepers of mysteries, holders of questions that have not yet been answered. What truly happens at the singularity, if there is a singularity at all? Whether information is preserved or lost, or transformed in ways we do not yet understand. How quantum mechanics and general relativity finally come together in those extreme conditions. Whether black holes might connect to other regions of space-time through exotic structures, or whether such ideas are merely mathematical curiosities without physical meaning. These questions wait patiently, as black holes themselves wait, enduring through the ages while generations of curious minds consider them with care. Estimates suggest that there may be 100 million stellar mass black holes drifting through our galaxy alone, each one invisible against the darkness of space, each one silently bending the light of more distant stars. Each one carrying its own history of the stellar collapse that formed it. They are everywhere and nowhere, common yet hidden, part of the galaxy's structure and yet mostly unobserved. Like quiet neighbors we rarely see but know are their damage. And beyond our galaxy, in the billions of other galaxies that fill the observable universe, countless more black holes drift and merge and grow. An entire hidden population that we are only now beginning to count and catalogue through gravitational waves and subtle astronomical techniques. And so, as you rest now, perhaps you might carry with you a sense of gentle wonder, a peaceful awareness that the universe contains these remarkable objects, these dark and patient presences that hold so many secrets and ask so many questions that we may never fully answer. There is no urgency to these mysteries, no deadline by which they must be solved. Only the long, slow turning of cosmic time and the quiet continuation of curiosity wherever curious minds exist. The black holes will still be there tomorrow, and for trillions of tomorrows after that, and the questions they inspire will continue to invite contemplation for as long as anyone wishes to contemplate them. For now, let the mysteries drift alongside you, gentle companions in the dark, as you settle into rest and allow your thoughts to grow still and soft, like starlight bending peacefully around a distant, quiet, enduring black hole.